program that where this collaboration that this is all part of died to me completely unexpectedly while I was preparing my lectures. He's been part of my mathematical life since he was the first person to unsolicitedly offer me a job in the 1960s, the end of the 1960s. It was a different time then. You people wouldn't understand it. There were jobs for everyone. Everyone was being offered jobs all the time then. But nevertheless, he's been a very big part of my life. And I'm somehow sad to see everyone speaking of him as in terms of what he did in the markets. He was a person who had very many sides to him. And I think we should all remember him. Anyway, I'm going to try to give you a point of view on quantum field theory. And I suppose my first lecture may be rather chaotic because I really did want to try and give some kind of point of view or overview, kind of starting from the beginning. My next three lectures, I'll say a little bit more about them at the end of this lecture, are rather more specifically focused, I hope. So I'll plunge in straight away and with my point of view. So first of all, let's start with classical physics. In classical physics, you see, we have to somehow, what's quantum field theory all about? Classical physics started assuming one knew what space was and what time was. So one was given a three-dimensional manifold, which was space, which was just there, and one knew all about it, and it was not going to change or do anything. And time was also a sort of copy of the real numbers, which was there and wasn't going to do anything. And in that framework, one built up physics. And one began something like this. One was studying a system which was, maybe I should have a piece of chalk handy. So one began, say, with space and time. But then one was studying some kind of system. So, for instance, one was studying three particles moving around, attracting each other by some forces or whatever. And so out of this, one constructed from M some configuration space of some physical system one was going to study. And this was constructed out of that in some way, because the only way we can describe anything is by placing it in space. That's how we interpret the world. And that we're stuck with that. We aren't going to be able to find any other way, I think, of describing anything that goes on in the world. Well, then one had to, there were some positions one's system could have. And then it was going to have some dynamics, forces that were going to act between the particles. And that was described by giving what I think of as a generalized Riemannian metric on this. So we were given a Lagrangian, which is a function on the tangent vectors to this. And I'll think of it as a generalized in the sense that it's a positive inhomogeneous quadratic on tangent vectors. So a Riemannian metric is a positive homogeneous function on tangent vectors. If we allow lower order terms, we get something a bit more general. And a Lagrangian is something of that form. And that's meant to describe completely the dynamics of the system. And out of this, we arrive, one of the things that this does is that this defines the symplectic structure omega on Qx. So this becomes a symplectic manifold. That's something with a closed two form. And that defines a Poisson bracket. That's a Lie structure, a Lie algebra structure. On the smooth functions on this. And classical dynamics, so this leads us to the concept of a classical dynamical system. Which consists of a symplectic manifold. That would be Px. The skew form that it has. And sorry, I should have said one more thing. When we got to this point, classical physics then tells us that in time, the system changes by moving along a geodesic with respect to this metric. For instance, if this were just an ordinary Riemannian metric, we would go along a geodesic in this space X. We go along what you might think of as a generalized geodesic if we have these lower order terms. But another way of saying that is that this goes the system determines a function in this, which is closely related to the function L we had here. This was the Lagrangian. And the way in which the system evolves is to say that any function on Y, such as this, generates flow on a symplectic manifold. And one way of describing the flow is that if you have any other function in that, its rate of change is given by the Lie bracket of H with F. Now, the original point of view on quantum theory was that when you started off with this system, you had to change it according to the prescriptions of quantum theory. And the prescriptions of quantum theory were that you replaced this classical dynamical system by a quantum dynamical system which consisted of an algebra A. In fact, it will be a topological algebra, but I won't need to go into that for the moment. It's an algebra with a star. That's an it's an algebra over the complex numbers. It's going to have a star. That's an antilinear involution, algebra involution. So a map which reverses the order of multiplication and is complex antilinear. And also an element H, which is going to determine the evolution. So we're going to replace this kind of triple by this kind of triple. And this is also this was, of course, a non-relativistic description. So it's in terms of a pre-relativistic picture of the world where the universe happens in space and just evolves in time. And here, the way, if we take an F in the algebra, then again, it's going to evolve by exactly the same equation, except we're going to put an I and a Planck's constant. So we're going to replace that equation by that equation. Let me just say one word about that. This is the first time complex numbers occur. And I think one of the great mysteries of quantum theory is why quantum theory can't exist without the complex numbers, whereas classical physics, you can introduce the complex numbers if you want. It may help in writing Fourier transforms and things more systematically, but there's no particular reason why here we should consider anything other than the real numbers. And think of that in terms of this thing. Supposing our algebra, now these are meant to be related in the sense that this A is meant to have something to do with the functions on Y. Now, if this were a commutative algebra, then of course this would vanish, and an antilinear involution would simply be an automorphism of the algebra which was antilinear. It would just be a real structure on the original algebra. So what this would be if A were commutative is simply a real commutative algebra. And of course, a real commutative algebra is essentially just the same thing as a space with suitable assumptions for even a manifold. We'll come back to that later on.
Great. Just the H and the F are functions on X or TX, just about.
Here.
Yeah.
F is a function, sorry, that should have been on Y. Yes, that's you're right. Thank you.
Y is TX.
And that also should have been on Y. And Y was TX. Thank you. Right. So you can think of this bit of the structure as saying that we go from a real algebra to a complex algebra, but at the same time we introduce some non-commutativity and everything starts to move. The complex numbers are somehow, it's a sort of fancier notion of a real structure. So that's one way of looking at that kind of quantum theory. Now, of course, originally in quantum, the systems that people had in mind when quantum theory was first studied were finite dimensional systems, things with finitely many degrees of freedom. So these manifolds were self-evidently, so to speak, thought to be finite dimensional. This picture, in any case, can't be taken over completely to modern physics because it's intrinsically non-relativistic. It singles out the spectral role for time. But even apart from that, well, so what was to be the original link between these two things? This was going to be a slight deformation of the functions on Y. This we've already mentioned, the rest of the structure. And the relationship between the two was meant to have all kinds of properties which are very easy to describe geometrically. For example, this structure defines a volume for a power of this on any symplectic manifold. So whenever you have a function, you can whenever you have a function, you can look at the volume of this space where that function is less than something or other. And that was meant to correspond to the number of eigenvalues of the algebra of this, the corresponding element of this algebra below a certain amount. So there was a complete pairing off of the properties of this and this. Now, so we have to now think what happens when we introduce relativity. in relativity, we can no longer have systems with finitely many degrees of freedom. Even if you wanted to just have two particles moving about, somehow trying to attract each other, then because in relativity, the influence of one thing on another isn't instantaneous, but happens with the speed of light passing between them, in order to know what any particle is going to do, it's no good just knowing where the other particle is at the time you're interested in. You have to know all that it has been doing for a little bit of time in the past. So there are no finite dimensional systems which are relativistic. People discovered that long ago. Of course, from another point of view, more modern point of view, it's also connected with the fact that the Poincare group has no finite dimensional representations. Other axiomatizations. So we're automatically into infinite dimensional systems. Well, this is stated in a non-relativistic way, but you can see lots of reasons why things are going to go wrong. For example, all of this stuff about differential equations, once you have infinite dimensional manifolds, it doesn't make the same kind of automatic sense that it did before. Vector fields can't necessarily be integrated, that sort of thing. So there are lots of reasons you'd feel suspicious of this. So the original point of view on quantum field theory was that we had still a classical system. For instance, it will be described by some sort of functions on space-time. So for instance, the simplest case would be, say, a scalar field where the configuration of the system was say, a smooth real-valued function on space-time. And we would try to make a quantum system out of that. And then we would sort of somehow try to interpret it. And that proved to be completely the wrong way to go. But nevertheless, that's what we have to explain. Now, in what way is it completely the wrong way to go? The first thing is that if we took that sort of hydrodynamic picture seriously, the mathematics of quantum field theory would be totally different from what it is. If, for instance, you think of this field on space-time as something like a water wave or something like that, then you would have an infinite dimensional manifold of configurations. But mathematically, it would have completely different properties from the properties of a quantum system, and much, much more difficult ones from the point of view of PDEs and mathematical analysis. Because what actually happens when you quantize quantum fields, as we'll discover, is that, well, you see, supposing you had Y is a space of fields, we'll come back to what that is on space-time. Maybe satisfying some equations or whatever. I just want to say this in very general terms. Then what should A be? Well, you might think it should be the functions on these things. And well, we'd have a reversion. Sorry, that's not column. Yeah. So then we'd have some. Well, we do indeed want to have that, as we will see. That's definitely part of the picture. On the other hand, we're going to make an algebra, which then you might think is going to have something to do with functions on this. But in fact, what this looks like is the functions on something very, very different. For instance, if we were actually looking at, let's suppose space-time with some manifold M naught there with space without time. So think of this being, for the moment, something like M naught across time, then whatever kind of functions you put on the space of functions on this is a complicated question, but this looks like the functions on almost finite dimensional manifolds. And one which is filtered by some kind of in some kind of way that, well, we're going to have A in A, which is going to correspond to this in the same way as we had before, the energy function, and this is going to behave like the functions on, well, I'll tell you what it's going to behave like. A is going to resemble, in the simplest case of a single scalar field, where this configuration space sub n of n naught is the space of sets of n unordered points in n naught. And this fix. And we're going to have a function h. H is going to look like a function on this, which if you look below a certain value, will vanish outside finitely many of those. Well, so it's going to look as if we're studying functions on a space which is infinite dimensional, but it's infinite dimensional in the sense of being a union of finite dimensional expanding pieces. Well, so in other words, what we have to do is find a completely new way of going between this picture and this picture. And one way that you can't do it, it seems, is full on trying to make a quantum system in that sense. I've said already that that is intrinsically non-relativistic, but you need to do something more drastic with this picture in order to get from one thing to the other. One of the things, for instance, which people have, because I went to the meeting connected with Witten's getting the Hamburg Prize last year, I heard lots of lectures from exciting young people in quantum field theory. And one of the things now is very much about considering the size, the sort of entropy properties of these algebras and the growth of the states and so on. And one of the bodies of papers which I saw people were now interested in was precisely about this kind of question. When we try to understand the relation between this and this, we have to start again trying to think of how we're going to associate a kind of what I think of as an ontology to this quantum, whatever it is, quantum system, quantum field system, which is somehow rather different from the classical kind of ontology. And what it amounts to is trying to spread out, think of ways of taking something like this algebra and thinking of it as somehow spread out, think of ways of spreading it out. And in some very vague way, some kind of decomposition of the algebra as a product of different algebras just associated to the different bits of space-time, different points of space-time. Now, obviously, one isn't going to be able to do this, but there's now a body of papers that I can perhaps later give people references if they're interested, in which people consider, given an algebra and maybe one particular element in an H, which is going to be a Hamiltonian, how can one write this algebra as a big tensor product? People produce finite dimensional analogs of these things and even apply computers to them in such a way that there'll be a natural metric induced on the pieces of the decomposition in which the distance between the x's is connected with the way the function h makes the different OX's interact. Anyway, that's not what I'm going to do. But of course, there's a very long history of trying to take some algebra of things which you're thinking you might be able to measure in quantum field theory and spread it out over space. The best known historically is what's called algebraic quantum field theory, where you take space-time M and you consider open subsets U in this, and you try to introduce a family of algebras which are associated with the different bits of space-time, and you can axiomatize that system. That's very much associated, for instance, with Hard. And that's, in some sense, a sort of version of what I'm going to be trying to talk about. Anyway, now it's time to get on to my main theme then, which is there's a rival way of trying to introduce some kind of axiomatization or ontology of quantum field theory, which is rather different from all the classical ones. Now, here we singled out a role for time. So somehow, if you're going to do anything relativistic at all, you see, it's very natural to think that whether space-time will consist of spaces at each time, and there'll be a bit of space-time intervening between one thing and another. And instead of just describing a time evolution, you should describe something associated to this time, something associated to this time, and some way of getting from one to the other. Now, the surprising thing is that you can do that and get quite an interesting mathematical concept. So we can introduce, I'll just throw it at you, I'm sure most people here have heard of it anyway. We can define, or try to define, the quantum field theory as something which seems at first a surprising thing to do, as a function from the cobordism. So we're going to describe the quantum field theory for a certain dimension of space-time. So I'll put N to D to describe the dimension of space-time. the theory for what's usually called the d minus one proportion category to vector spaces. So this is vector spaces. In fact, being topological. And what do I mean by this? And of course, they'll be infinite dimensional. So, what does this mean? Well, we're going to consider a category whose objects, so this is a first crude approximation, d minus one dimensional manifolds. So you think of them as being space-time at some particular time. And there are going to be various versions, maybe even compact, or maybe compacted boundary. And to each one of those, one's going to associate something which, roughly speaking, you can think of as like a Hilbert space. If you're used to the Hilbert space formulation in quantum mechanics, that's meant to be sort of the Hilbert space of your system. We're going to have a different one for each time. And to a cobordism, that means to something which I think of as like this, but maybe also, for instance, like this. From some other m, it will be a d-dimensional manifold. All my manifolds in this talk are going to be assumed to be oriented. We will associate to each thing like this, for m0 and m1. The vector space em0, a vector space em1, and some operator, which I'll call u of m. So this is m of the overall space time. Now, there are lots and lots of questions to ask about what kind of topological vector spaces, what kind of cobordisms, what kind of manifolds, and a lot of that is going to be the subject of my next 3 lectures. But for the moment, let's not. Let's consider this in very general terms. One of the things that makes me interested, quantum field theory is a very, very diverse subject. One can be interested in it from the point of view of studying fundamental physics, the ultimate kind of what goes on, how to describe the universe at its fundamental level. And it's obvious from what I've said so far that that's the aspect that interests me. But there are many, many other areas in which quantum field theory can intervene. Like, for instance, quite independently of space-time, it can be some kind of continuum limit of a lattice model in statistical mechanics. Or it can be, the lattice might be something on which information is flowing in some kind of quantum computer or something like that, then you might be considering quantum field theory in that situation. So there are many, many different places you can start looking. And the motivation is rather different, and the kind of questions you're interested in are rather different. And I'm certainly going to be oriented towards one of them. And so I don't want to suggest that there aren't different and equally interesting things that would somewhat contradict some of the points of view I'm going to try to persuade you of. Looks like I've come to the point where I have to raise. Yes, I said that to introduce the fact that one of the things I most want to, I've got an extremely well-known remark that quantum field theory describes the world except for gravity. And gravity is about the dynamics of space-time itself. And so in classical physics, we assumed we knew all about space and time before we started. And quantum field theory, people usually assume that you know all about space and space-time before you start. But one of my themes is that that isn't really quite true. Quantum field theory actually helps you to understand the possible ways space-time can be. It isn't just neutral with respect to what kind of thing you feed in. And I want to try and illustrate that point. So that's something I'll be talking about mainly in my very last lecture. But you see, in this definition that I'm giving you, you can already see a problem. Because, well, from that point of view, in that I have said we'll take a cobordism category and a functor in topological vector spaces. So you may say, well, I've already fed in my space or space-time, so I've already assumed that, and I'm not going to find out anything about it. But one of the things that I'm going to sort of tell you some advantages and disadvantages of this definition. One of the things that attracted me originally to this definition is that it tells you what a quantum field theory is, and thereby, for example, gives you an absolutely on-the-nose way of deciding whether two quantum field theories are the same, so that you can describe a moduli space, in principle at least, of quantum field theories of a certain kind. In other words, we know exactly how to vary quantum field theories. Now, you see, one of the things that, supposing we were trying to make a theory that included gravity, then what we would want to do, in some sense, is assign a quantum system to some things that happened on space-time, but also included the moduli space of all the possible space-times. Well, one would like this to be some kind of big, something like a manifold. And so the moment we start being able to talk about a moduli space of these things, we start having a kind of space being given to us, which might be somewhat different from the spaces we put in. And you see, this gives us a feedback process between the two ends. You see, by trying to make those two things somewhat the same, one is homing in on the notion of space-time. So let me now just, before going any further with that, I have to stop before 11, don't I? That's the destination, is that right?
11. Around 11, yeah.
I'd like to make a remark about some ideas of Kohn on this subject. Kohn was simply, at least first, interested in saying, well, yeah, well, let me say something, first of all, about the very, see, one of the themes of this lecture is to try to say something about non-commutative geometry from certain points of view, how it sits, how it relates to ordinary algebraic topology. We suddenly have thrown away commutative algebras, which everyone understands are related to space, because a commutative algebra is more or less the algebra of functions on its spectrum. The non-commutative things, well, what kind of ways what's geometrical about them? Well, the first thing is that in quantum field theory, we have this element of the algebra given to us, H, which is going to be a positive self-adjoint element of the algebra. That's going to make a very big difference because we, being human beings, only see things that are moving very slowly. We can't even see a bullet, let alone kind of things that go really fast. A bullet is stationary from the point of view of the general perspective of the universe. We only see things that go very slowly. And whatever our idea is, somehow the rate of change of whatever's depicted by one of the elements of our algebra is connected with how it commutes with this given object. Well, when you have one element, which probably, these are very big algebras, we'll have a thing with a huge diverse spectrum. If we diagonalize it, it's meant to be a self-adjoint positive element. Things which almost commute with such an element are going to have to be pretty nearly diagonal. So we're concerned with algebras which are pretty nearly commutative. Well, now some of you will want to jump ahead and say, but we're interested in topological field theory where this element H is 0. So everything then is completely different. You really do, in principle, have a general non-commutative algebra. You are into serious non-commutative geometry. But again, quantum field theory is about algebras which are nearly commutative. And that's an important thing to hang on to. Well, so now let me pursue that definition a little bit more. The first thing you can, sorry, no, sorry, getting confused. I wanted to put in the remark about Kohn. So Kohn was interested in describing, first of all, how you could characterize the algebra of functions on a smooth manifold by properties of the algebra. And the emphasis there should be on the word manifold. Right? A manifold, first of all, has certain local structure. It looks like Rn. When you think about it, that's very algebraic. If you want to say what it means for an algebra to look like functions on Rn, that's saying that it's freely generated by n commuting variables. That's a completely algebraic property, which is very difficult to express in any other kind of form. But being a manifold also has a global property because a manifold has Poincare duality in its topology. And so there's also something connected with the global properties of the algebra, not connected with what happens at a small scale. And Kohn was interested in making a concept which got that exactly right, characterized the functions on a smooth manifold, and lent itself to non-commutative generalizations of a fairly mild kind. Now, the kind of algebras that he was focusing on, certainly to begin with, were he took some space-time and then considered a bundle, I call it B, on an ordinary manifold M, where at each point, so this is we have, and at each point, this was a finite dimensional algebra. And so it was something like a finite, an n by n matrix algebra, but it's going to be also going to be a module. It's going to be an algebra over the Clifford algebra of the tangent space to M. So I won't even say for the moment what the Clifford algebra is, but well, it's the algebra associated to a finite dimensional vector space with an inner product. This is meant to be Riemannian. It's the algebra generated by an element gamma psi for each psi in the tangent space with M, and gamma psi squared is just going to be the length, the Riemannian metric of that. You might want to put in a minus, but that doesn't matter at the moment. So this algebra is going to contain this algebra. And so you can think of an, and he also wanted a connection in this bundle. So if you have this and a connection in this, you can define a Dirac element, a Dirac operator, which at any point is we had a connection giving us a basis for that tangent vector. We can define a Dirac operator, and this is going to be something. In fact, the Hamiltonian element in his algebra is then going to be this thing squared. I should really put the minus in there. I think we can change the conventions, but so he considered setups like this. Now, in fact, these are the kind of things that we are going to contemplate putting in to our cobordisms. In other words, we're going to have things like this as our space-times, and we're going to get out things which are somewhat like this as our space-times. Kohn did things which he made. He produced a version of the standard model of quantum field theory in this picture, and most physicists really don't like it for lots of reasons we won't go into now because it's a bit too pat. But he did some very interesting things. For instance, he defined a kind of operation of forming a trace of this operator. And he got a formula for that in terms of the structure. And for suitable choices of these bundles of algebras, he got exactly the kind of thing that you get in a standard model Lagrangian. You get the ordinary Yang-Mills term for a connection, but you also get the natural Einstein gravitational action. The thing that really impressed me was that when you made this algebra a direct sum of different finite dimensional algebras, so that it wasn't a simple algebra, but had different components, then just using the natural thing here, we got a Higgs field. So the thing that's really strange, for me at least, in quantum field theory is indeed this Higgs field, which suddenly introduces a quartic potential or something, which to me, doesn't fit in with the ideology at all. And Kohn observed that this Higgs field comes naturally from choosing this algebra. Anyway, that's just a remark. Now let me try and tell you very quickly some I'll just have to say them rather quickly. I imagine they're rather well known mostly anyway. What can we do with this kind of structure? Well, in my second lecture, I'm going to be concerned with the kind of vector spaces and the kind of operators and the kind of structures on the manifold. But let me simply talk about the very formal properties first of all. So supposing we had a functor of the kind we're talking about, then we have something which we think of as space line. Where are we going to get local algebras from? Things they're going to, where are we going to get any kind of algebra from? Well, one of the things we can do is if we had some points in this space-time that we're putting in, this is our M, the cobordism from M0 to M1. Supposing we have some points here, then we can make a little hole in the manifold around each of these points and take that out. And then we can say, let's just define OX, a vector space, which is the E for the boundary. So supposing here is a point X, and around here we have some, the bit that we've cut out is some little disk, some little ball dx. Then this is just a vector space.
The boundary.
But, sorry, boundary. The vector space associated to that. But when we take out all of these points, we can think of this as a cobordism from M0 disjoint union, the disjoint union of the boundaries of these dxi's. And this will be a cobordism in that. I'll write it like that to show it's a cobordism. M1. So we started off with just an operator from a vector space to a vector space. Oh, sorry, I didn't even tell you. Really beautiful. At least one thing that I should have said right at the beginning was the property that this is going to have is that it's going to take disjoint union is going to go to tensor product. So these axioms are going to take disjoint unions, here, the tensor product of this effect. Because we need to discuss what kind of tensor product. So the space associated to this will therefore be E, the tensor product over R, with all of these OXIs. Now we want to imagine this as being very small disks that we took out. So this will associate. Now, if we were just in some sort of static space-time, you can imagine this as being the same as this. So it's what we really have just one big infinite dimensional space. You can think of those two things as being the same. And the neighborhoods of all these little points will also look the same. So all of these things will actually be the same. So they're just different copies of the same thing. So what we are getting is a lot of operators from here defined by things in this vector space, which can be put together according to concatenating those cobordisms. Now, this isn't an algebra of operators, because this isn't something we can multiply. So we've already got out of the situation where we have any kind of algebra at all. But what we have is a higher algebra. We are in a space, imagine it's RD. Whenever we have a finite collection of points, we have something O which we can associate we can take elements associated to a lot of points, and we can somehow compose them according to that diagram. So we have, in some sense, composition laws which are not defined, or one composition law for each way of choosing a finite number of distinct points in a small neighborhood. Now, if you could push all these together to one point, you see, we would, and if they then coalesced into one single thing, we could make an actual algebra. But so what we have is something with a family of composition laws, parametrized, at least if we're just looking just at the very local situation, just imagine that we're only interested in what happens in a little patch of things. We're looking at representation of something which is where the multiplications are parametrized by a group of near together points, which aren't allowed to be exactly together. That's the typical example of a higher multiplication, and supposedly one of the themes of our meeting. So we get this structure. I've only got 5 more minutes. So the situation where this perspective worked brilliantly was for two-dimensional theory. This is what it was originally applied for, invented for. And I'm just going to say a few words about what happened in that case, because it's very well. One thing probably, well, these structures have a lot of properties. For example, supposing the simplest example would be, probably everyone will know this already. If we do this with d equals 2, so our manifolds are bunches of circles, all circles-oriented circles are the same. So we have just one vector space, and we have a multiplication on it corresponding to a cobordism which looks like that. And we have a special element in it corresponding to a cobordism that looks like that. And we have a trace or something looking like that. And probably, if you just simply consider this on the cobordism category of smooth manifolds without anything else other than orientations, smooth compact manifolds, then probably everyone knows that what you get is a finite dimensional Frobenius algebra. A finite dimensional Frobenius algebra is a finite dimensional complex vector space with a map like this corresponding to that cobordism. X1. It will have an element in it corresponding to this, and a form on it corresponding to this. And the fact that it's a Frobenius algebra is simply the fact that the pairing is non-degenerate. There's non-degenerate pairing on that vector space. So this is a kind of algebra with some kind of duality. And the wonderful thing is that when you put in some more realistic category, you actually get the greatly generalized version simply of a non-commutative algebra looking very like, looking somehow very like something like the functions or even perhaps the differential forms on a manifold. And picture which emerged, and which was the motivation originally for string theory, was that the totality of two-dimensional field theories, in the sense I'm going to give more details of in the following lectures, looks very like the category of Riemannian manifolds of arbitrary dimension, and even better, so they have a moduli space, which is pretty, well, certainly the way I got into the subject was to try to produce a definition where you could define, in principle, a moduli space of two-dimensional field theories and prove that it really did look something like the space of two-dimensional manifolds in such a way that now on any theory where at least the manifolds have a Riemannian metric, you have a flow on the theory coming from rescaling the metric. And this was studied in two-dimensional field theory, and people discovered, to their surprise, that that was essentially the gravitational flow on the Riemannian metric. There was a vague idea of how to set up a correspondence, the so-called sigma model, between manifolds and two-dimensional theories, and the scaling flow on it was the gravitational flow. This was in one of the many versions of string theory. You know, string theory is a subject which changes character every few years. There was quite a stationary phase, a sort of point of inflection, where for quite a long time, that was the motivation of string theory, that two-dimensional field theories were the good model of the space of manifolds on which the gravitational flow was beautifully defined. It's time for me to stop now, and I haven't quite got to the point that I wanted to, but so let me tell you, the next 3 lectures were meant to be systematic things. So the next lecture, all the nice properties which tell you the difference between the input of a space of fields and the output of a space of particles, roughly speaking. All of that is because, essentially, of the property of positive energy. And my next lecture this afternoon is meant to be about the positivity of energy and how you formulate that in quantum field theory. My third lecture was meant to be about scaling. One of the things that is crucial is the way we're near commutative algebras, and we have to measure the distance we've got away from. And then my third lecture will be much more like algebraic topology. It's meant to be about what category of objects do we really want to put in here. So what is a sort of candidate category for the good models of space-time and of spaces which arise in fundamental physics in general. So I'll stop for now.
We have time for questions.